talk Ohm's law. Here is our current density to conductivity, right? If we have some little wire here, it has length A, cross-sectional area, length L, cross-sectional area A. That means there's a voltage across this thing. These would be equipotentials, okay? So if we have a voltage across this thing, that means there's an electric field going this way, which means the current goes this way, because remember, if you have positive charges, they're going to move in the direction of the electric field, so that's going to be the same way as the current. And it turns out with a little bit of math, we don't have to go through all of it right now, this can be rewritten as delta V is equal to IR. Okay? You can see the I is going to come from the current density. You can get delta V a little bit from the electric field. There's some derivation where we plug in resistivity and we figure that out, but this basically comes from that. And this is conceptually useful, but this is much more practically useful because what do we measure? Voltage and current, okay? So knowing how voltage and current relate to each other is a lot more useful than knowing how current density, which is harder to measure, and electric field, which is very hard to measure, relate to each other, okay? And we've already done a lab where we checked this, and it worked pretty well, okay? So here's our resistance. Remember, resistance is in ohms. It turns out an ohm can be broken down into a volt per amp, which comes from Ohm's law, okay? So here's our Ohm's law. Remember, along a wire, you have a particular resistance. In a circuit, right, we just treat resistors by their resistance. We don't have to go through all of this, okay? That's predetermined. When you get a resistor, you can just read its resistance. You don't have to be like, well, what is this resistor made of? And how long is it? And what's its cross-sectional area? It turns out since it's already created, it's already got a built-in resistance. So in circuits, we deal with Ohm's law, okay? So here's our battery. We have a resistor element that uses up power and a battery that produces power, okay? So we have a voltage difference, let's say 0 to 1.5. That means everywhere along this wire, the potential is 1.5. Everywhere along this wire, it's 0. And then that drops across the resistor, okay? And an ideal wire, of course, has a resistance of 0, although we know that's not completely true. It's a really good approximation for most cases, and a potential difference of 0 also, okay? Oh my God. Let's see. Do you want to do this problem? Yeah, we're going to do this problem. So, we'll do it together. Given the resistance of a typical human body, that's about 200 kiloohms, how much current would flow through a person if he or she is shocked by a taser charged to 50,000 volts? Exactly.
All right, so typical human body, if you add up all the resistor arms and legs, the resistance of a human, we can approximate, very approximate, to be 200 kiloohms, all right? And we want to know how much current would flow through a person if you tase them. So here we have a taser, and it has a voltage of 50,000 volts. And we're going to see, and obviously it's going to depend on where you tase them, but just generally treat a human as a resistor. We're going to use our equation. And which equation are we going to use? Well, probably Ohm's law. So equation delta V is equal to IR. And we want to figure out the current. So current is going to be delta V over R. We'll plug in our values. So we have 50,000 volts. So that's 5 times 10 to the 4th volts over 200 times 10 to the 3 ohms. So that's the 200 kiloohms. You put that into a calculator, that gives you about 1/4 of an amp. Or you can call this 250 milliamps. And just for some reference, this could be deadly. I mean, if you get it in the right place and you have this current for a certain amount of time. But it turns out the current is actually limited by power. And power is equal to IV. Sometimes this is a function of time. We'll learn about this in a bit. But because of this, it won't actually kill you unless you have like some sort of pre-existing condition. And so even though we get 250 milliamps, and here's some references, right? So 1 milliamp, shock. 10 milliamps, pain, muscle contractions. And then 150 milliamps, if you have it for long enough, you can go into cardiac arrest. So you'll see this is bigger, but there's a little bit more to it than just the current at a particular time. This current happens pretty quickly. You're just trying to disable somebody, not kill them.
Actually, I should change that next part of the thing. I want to take a break. But just as a reminder, circuit diagrams. This looks like a battery. This is a wire, resistor, light bulb. Okay, we sort of went over this in the lab. So for instance, here is a really basic series circuit. It's a battery and a resistor. The current's going to flow this way because we consider current to be the flow of positive charges, which is wrong, but not wrong enough to change it. And yeah, so the government? Did you just say the government? Okay, try drawing those using the stuff we know about circuit diagrams. So generally, hopefully, this is what these things look like. Let's take a break. We're going to need a break. Come back in about